Machine learning models perceive data as geometry. When an embedding model processes text, images, or audio, it translates that raw information into a dense array of numbers, a vector, typically containing hundreds of dimensions, like 768D. Finding meaning in the space requires semantic search, which identifies the closest geometric match to a query using a metric like exact cosine similarity. This brute force approach calculates the distance between the query and every single point. In computer science, this O of n operation is the equivalent of searching for a contact by flipping through every single card in a massive physical Rolodex. Traditional relational databases and B-tree indexes are built for scalar values or alphabetical order. They are oblivious to geometric closeness in a multidimensional space. Modern production environments require scanning 1 billion vectors and returning the closest matches in under 20 milliseconds. For high-dimensional data at this scale, exact retrieval is a mathematical dead end. The architecture has to change. This scale is the reason for the vector database, a storage engine designed specifically for spatial relationships and multidimensional geometry. To maintain speed, vector databases move away from the guarantee of exact spatial retrieval, relying instead on Approximate Nearest Neighbor search, or ANN. By accepting a microscopic fraction of recall loss, ANN algorithms can reduce search times from minutes to milliseconds. Instead of a Rolodex, this functions like modern navigation. A query point snaps to a pre-calculated highway route, reaching its target in a few algorithmic hops. ANN pre-calculates this topological roadmap, an index, routing the query without evaluating the entire database. The actual performance of a vector database depends on which specific algorithmic architecture is chosen to build that index. ANN search acts as the engine of the database, providing the algorithmic speed necessary to handle production-scale workloads. One of the most prominent architectures used in modern search is HNSW, Hierarchical Navigable Small World. This diagram shows the core of HNSW, a multi-layered proximity graph where vectors are connected to their closest geometric neighbors across different elevations. A query enters at the highest, sparsest layer. This acts like an express elevator, traversing massive geometric distances instantly to find the general vicinity of the target. The query then drops to the middle layers, using shorter connections to refine its position within the graph. Finally, it reaches the densest layer at the base. These are the local corridors, where the query takes its final few steps to lock on to the exact nearest neighbors. This greedy routing mechanism shrinks the search radius logarithmically at every step down the tiers. By navigating the hierarchy rather than the full list, HNSW reduces search time to O log n. As a dynamic graph, HNSW also supports incremental, real-time upserts, allowing new data to be added without a total index rebuild. However, maintaining a traversable, multi-layered graph across billions of points requires significant hardware resources. HNSW addresses the latency bottleneck while introducing a severe memory overhead. For HNSW's logarithmic traversal to work, the entire graph must reside in active memory, the RAM. Storing raw 32-bit float vectors and the complex edges for billions of points can quickly consume hundreds of gigabytes or even terabytes of RAM. Operating at archive scale, above 10 billion vectors, using purely HNSW becomes financially prohibitive for most organizations. When memory constraints outweigh the need for peak latency, architects must move away from graph-based structures and toward data compression. This leads to the second dominant algorithm, designed for memory-constrained, massive-scale deployments, IVF-PQ. The first half of this system is the inverted file index, or IVF. It partitions the vector space into discrete clusters around central nodes called centroids. When a query arrives, it only calculates its distance to these centroids, selecting the closest zone and ignoring the rest of the database entirely. But even within a single zone, millions of full-resolution vectors are too heavy for efficient storage. This is where product quantization, or PQ, is applied. PQ crushes the data by splitting high-dimensional vectors into subvectors and replacing them with short approximation codes. Instead of storing a full, highly detailed description of an item, the system now stores a tiny, standardized SKU code. The search query then performs a highly optimized asymmetric distance check against these tiny SKU blocks, rather than massive floating point numbers. This method is highly efficient, shrinking RAM footprints by 16 times compared to raw storage. This compression comes with a trade-off. PQ introduces a slight penalty to recall accuracy, and IVF clustering can slow down real-time insert speeds. System engineers can dynamically tune the size of the codebook to find the exact balance between recall loss and memory savings. IVF-PQ enables vector search to scale into the tens of billions by compressing both the search space and the data itself. There is no single best vector index. There is only the correct algorithm for your hardware constraints and latency budget. We can organize these choices into a comparative matrix. Default to HNSW when the application demands real-time streaming and highest recall, provided the RAM budget is available. Shift to IVF-PQ when crossing the billion vector threshold, where infrastructure costs must be managed through aggressive compression. The ecosystem is also evolving. GPU acceleration is increasingly used to speed up IVF-PQ indexing and the construction of HNSW graphs. Mastering vector search requires balancing the triangle of recall, latency, and cost. Production-ready systems require one final layer of complexity: hybrid search. Semantic similarity is often insufficient on its own. Queries frequently require hard Boolean filters, such as finding similar documents only from a specific department or timeframe. The Digabase Query Planner executes this by applying metadata filters to slice away irrelevant nodes before or during the graph traversal. We have moved from the computational impossibility of ON scans to the efficiency of multi-layered graphs and quantized clusters. Vector databases map deep semantic meaning into navigable, multidimensional geometry, transforming a brute force mathematical impossibility into a millisecond reality.